Okay, so good morning, everybody. Have a wonderful morning. My name is Wolfgang Eigner. I'm a professor at St. Pölten University of Applied Sciences in Austria, and I'm very happy to welcome you here for this very timely topic, a session on temporal data. We have a lineup of 5 fabulous talks. I really have to say that I'm very much looking forward to that because they have all very different angles to the topic. And we will be starting off with a virtual presentation with the title, Visualizing the Passage of Time with Video Temporal Pyramids, and the talk will be given by Melissa Swift. And remember, if you have any questions, also already during the talk, don't forget to put it into Slido that we have them then for the Q&A session.
Hello, my name is Melissa Swift. I conducted this research while I was a graduate student at Western Washington University, studying with Dr. Scott Wehrwein. I am now a data scientist at Pacific Northwest National Laboratory, working on computer vision projects. Our research is titled Visualizing the Passage of Time with Video Temporal Pyramids. So if you record a single scene for months or years, you end up with a lot of video. And that video might have interesting phenomena that occur at multiple time scales, such as hourly, like traffic patterns, sun movements, or even monthly, seasonal changes, and yearly things like large changes to landscapes or buildings. So why not use standard time-lapse techniques? As an example, if you want to show the monthly time scale, that means choosing 1 frame per month, but your chosen frames may not be representative, much information gets discarded. Also, there are flickering effects from aliasing and temporal discontinuities. As an example, here's a time lapse of the monthly time scale. And as contrast, here's our temporal pyramid video of that same scene in the monthly time scale. So our 2-part approach is to first create a video temporal pyramid, where each level of the pyramid is a new, shorter video that distills a certain time scale, and then to visualize everything in a video spectrogram tool, which allows for navigation and discovery of patterns, etc. Some related work that we looked at were obviously time-lapse and related techniques, and there are some interesting attempts to smooth out the discontinuities after having discarded frames, but our method actually doesn't even need to discard frames in the first place. Video visualization is clearly related, but most research is primarily focused on short videos, minutes or hours, and it generally has different goals, such as fast forward or anomaly detection. Interactive video exploration and retrieval is mostly about finding specific content, not general discovery, and it's about getting a visual overview of a relatively short video. And of course, time series visualization is relevant, but video is unique and requires domain-specific techniques. So let's get into how we create the video temporal pyramid. We were inspired by the concept of image pyramids from computer vision, which blurs an image, then subsamples the pixels to create a smaller image, and each level of the pyramid gets smaller and smaller. Gaussian pyramids keep the blurred images, and Laplacian pyramids keep the difference. So let's do this in the temporal dimension instead of the spatial dimension. So building a temporal pyramid starts with this long source video. We read the video frames and apply a blur kernel, and then we get a blurred video, which we subtract from the original to get our Laplacian difference video. We also subsample the blur video to create our Gaussian blur video, which is shorter because it has fewer frames. Then that's building one level of the pyramid, and the next level starts with the Gaussian blur video as the source video. So we continue recursively building levels of the pyramid. I'll now show you an example of what these Gaussian blur videos look like. This is a scene from the Bryant Park skate rink in New York. So this is the 1-second time scale. This is the 15-second time scale. Things are moving faster, and there you see the Zamboni cleaning the ice. This is the 5-minute time scale. where we can actually see the whole day go by in about 9 seconds. And here we see the 4-hour time scale, where interestingly, we don't see any people moving around because they aren't moving slow enough to be seen. Now we'll talk about the video spectrogram tool, which is addressing the problem of too much video. We needed a way to navigate through time and timescales, hone in on events of interest. Our central idea is to use the Laplacian difference frames and take the L2 norm of the pixel values as proxy for the magnitude of change per frame, and then we plot that as a spectrogram. This is what our user interface looks like. We have an overview spectrogram on the right with the level highlighted that we're viewing, and we have a drop-down menu here where we can choose different timescales. The video for that level will play, and as the video plays, there's an orange line that tracks along the frames here, so you can match where you are in the video to where you are, to what the spectrogram looks like. Here you can see some areas of missing data. Also, if you hover your mouse over here, the thumbnail down here will change, and this thumbnail also has date and time information. So now I will highlight some interesting results. The spectrogram seems to be very good at visualizing cycles and periodicity. For instance, the Bryant Skate Park pattern of having the ice clear versus having lots of people and movement on the ice shows up as a clear temporal pattern in the spectrogram. And in this bridge data set, we see the drawbridge going up regularly, and each time it goes up, there's a bright spot in the spectrogram. We can easily discover anomalies, such as in this video. Oh, look at that. There was something unusual that popped up that we could easily view at the 1-month time scale. And then we could use the spectrogram to drill down and figure out when it was there, how long it was there, etc. Our videos also help with long-term dynamics and understanding, such as this coastline scene where we see the line of the surf here moving slowly. But this is a monthly time scale over a 2-year time span. So it's not the daily tidal pattern, but longer term cycles and trends. We also did a direct comparison of time-lapse versus our pyramid videos. In this time-lapse, the aliasing makes the traffic seem chaotic and random. And in our pyramid video, you can see a regular pattern of the cars solidifying and stopping regularly, probably at an intersection, which is more information than you would otherwise get. To conclude, we have created a new way of viewing a scene over a long period of time with video temporal pyramids, distilling each timescale into a shorter video, and video spectrogram, navigating and discovering patterns and anomalies and drilling down for more details. Some possible applications and implications may be visualizing long-term effects of climate change or urbanization, discovering anomalous events during surveillance, long-term monitoring of ecological sites, education, artistic possibilities, and perhaps even shifts in perspective towards long-term thinking beyond our normal human-centric point of view.
Hello. So Melissa, thank you very much for the presentation. Can you hear us well?
Yes, I can. Hopefully you can hear me.
Perfect. Yes, we can hear you well. Okay, so while you're typing in your questions, or you can also come up to the mic here and ask a question in person, maybe start off with one question. So reading the paper, it occurred to me that the temporal granularities used are tied to calendars mostly. So you talked about days or month. So would other granularities maybe also make sense? Like, I don't know, sunrise to sunset or something like that, that are tied to the application there?
Yes, and actually, yeah, we experimented with some data sets that had, like their webcam was only on for 16 hours a day when it wasn't even on during the night. So we had to account for that. But it should also be possible to just like take 8 hours of the day, of each day during daylight, and then build the pyramid from there too.
Okay. Are there any questions in the room? Yes.
Hi, Kuno Kotzarts from University of Stuttgart. So the examples that you showed are based for static cameras, right?
Yes.
How would this technique look like if you use, for example, long-term recordings from GoPro cameras while I'm on a trip or so?
Right. Yeah, I'm not sure it would translate well. It would probably be a kind of a body of work to figure that out. Like the main reason we can do this is because we're keeping the spatial variation steady, so that we can focus on the temporal variation. It would be difficult to tease apart spatial and temporal together, but hopefully somebody will do that.
Well, you can try to compensate a little bit for individual movement and then see what's left over.
Yeah.
That's a cool idea.
Yep.
I really like this presentation.
Thank you.
Okay, so thank you all very much for the presentation. Let's thank the speaker once more. So next up, we've got a live presentation here entitled Constrained Dynamic Mode Decomposition. The speaker is Tim Krake.
Can you hear me well? Oh, okay. Okay. Hello and welcome to my talk about constrained dynamic mode decomposition. My name is Tim Krake and this is joint work with Daniel Klötzel, Bernhard Eberhardt and Daniel Weiskopf. And let's directly dive into motivation. In time series analysis, a typical task is to decompose time series into seasonal and trend patterns. The shown time series records the annual lynx trappings in Canada from 1821 to 1934. Besides trend and seasonal patterns, the dataset also shows interesting cyclic patterns. To complicate the task of time series decomposition, we only use the last 70 measurements. Now we can apply dynamic mode decomposition, in short, DMD. In general, DMD is a spectral decomposition method that extracts spatio-temporal patterns from data. However, there's no parameter to influence the decomposition. Here you can see the results computed via DMD. And we already used our proposed filtering where trends and seasonal patterns are grouped and sorted by their influence. The superposition is shown top right, and you can see the mean absolute error, which is approximately 700. At this stage, the user can only interpret all the DMD patterns, which consists of periods, magnitudes, temporal evolutions, as well as superposition and the absolute error. However, the user has often access to additional knowledge, such as timescale patterns, or easily observed patterns, or external knowledge about population, decay, and growth rates. For this time series, you have knowledge about animal populations in North Canada, which have a period of 9.63 years. So now we would like to incorporate this period because DMD only detects the period 9.99. So this brings up the question, is there a way to adjust DMD? Can we incorporate this period? And the answer to this question is yes, and that is exactly what our method, constrained dynamic mode decomposition, is capable of. So before I start with a detailed explanation, I want to briefly outline the remainder of this talk. First, I will talk about some background stuff, including DMD and the application to univariate and multivariate data. Then I present our method, constrained DMD, along with the human-in-a-loop algorithm and the visualization techniques. And finally, I will show some result. We already saw the links data set, and I will compare them to other spatial temporal decompositions. So for the background for DMD, DMD aims to find a linear operator A that connects data in an optimal way. Mathematically, this can be expressed by a minimization problem that is based on linear least squares. In general, the matrix A is quite high-dimensional. So the core idea of DMD is to only compute the relevant spectral components of A without computing the matrix A actually. DMD achieves this by using a reduced singular value decomposition to obtain the low-dimensional representation S of the matrix A. And S is then used to compute the DMD output. The DMD components decompose the data into a sum of triples, which consists of DMD eigenvalues, modes, and amplitudes. And these characterize temporal, spatial, and dominant structures. However, for univariate time series, the matrix A is only a scalar, and therefore we run into a problem. So to account for this, we use the original time series Z0 to Zm and perform a delay embedding. With this, we obtain the delayed time series x0 to xm, and then we can apply DMD. DMD can then decompose the data, as we saw before, into a sum of triples. And these components can be finally diagonal averaged, and then we obtain the DMD components in the original space, which can be used for our analysis. This is the background to DMD, which our method relies on. So now the idea of our method is to update the low-dimensional matrix S, since S encodes all the information about the DMD components. For this step, we use an equivalent representation of the matrix S, which has the structure of a companion matrix. And this companion matrix has some nice properties. In fact, we have direct access to the characteristic polynomial, and therefore we could formulate an appropriate minimization problem to incorporate our frequencies. Since this part is a bit technical, I just want to outline the idea. So the current eigenvalues of S are encoded in the matrix G and B, and the desired eigenvalues, which you want to incorporate it, are encoded in the matrix G tilde and B tilde. So the desired eigenvalues are covered in the constraints. The matrix K is a scaling matrix, which is used to make everything practical. And this minimization problem can be easily be solved by constrained linear least squares optimization. The resulting matrix C tilde contains the updated DMD structures, and C tilde can then be rearranged into the matrix S tilde. And S tilde can be used to update DMD. And that is exactly the core of constrained dynamic mode decomposition. So now let's bring some visualization into the pipeline. Given the DMD output, we can directly visualize them. There are several techniques described in the literature, but we don't want to focus on that. We don't want to improve them. We only use them in the first place to give feedback to the system. With this, we have the first human-in-a-loop process to incorporate user-specified frequencies. To further improve the visual exploration with constrained DMD, we developed additional visualization techniques, a filtering technique, which we saw before, a clustering technique, and also a change tracking of eigenvalues, which is based on change tracking of the eigenvalues. Based on these techniques, the user can also give feedback to the system. So let's have a closer look at the visualization techniques. We already saw the filtering technique before, where all of the components are sorted by their influence, and then are grouped into the three categories: trend, seasonal, and residual. The clustering technique uses the frequencies of the components and computes superpositions of interesting harmonic patterns. These provide useful insights into the time series. You can find more in the paper. In contrast, the change tracking supports the human-in-a-loop process. So it tracks the changes of eigenvalues when DMD gets new user-defined frequencies. The visualization is rather straightforward in a complex plane with vector-like connections of old and new eigenvalues, and due to the ring-like shape, even small changes are visible. The correspondence problem is solved via a similarity matrix. that uses both the eigenvalues and the eigenvectors. So let's look at some results. Again, we consider the links data set, and we already saw the results with DMD. A slightly increasing trend, the main period 9.99, other periods without a reasonable structure. Now, since we know that links have a population rate of period 9.63, we want to incorporate this period as well as some harmonic periods to it, which are half the period times 2, and the period times 4. The impact of the incorporation is huge, as you can see. The main period 9.99 is replaced by the period 9.63. The last two periods close to 5 are replaced by 4.815, and the intermediate period 27.39 is now gone, and the periods 19.26 and 38.52 for larger scale structures appear. In fact, all of our user-specified frequencies are now integrated into the system, and the resulting superposition shows a clear improvement. And when we compare our method to other spatial temporal decompositions, such as STL and SSA, we see that our DMD patterns are linked to quantities such as periods, and therefore the components are much more accessible. In addition, STL and SSA do not produce a good variety of patterns. STL has only 3 patterns, and SSA rather concentrates on a best fit representation. So, in contrast, DMD produces a good variety of patterns, and the variety concentrates on a frequency-based representation. And with constrained DMD, now we have even bring an explorative character into DMD. And this makes time series analysis with DMD more accessible and useful. With these words, I want to conclude my talk about constrained DMD. The source code will be available on GitHub. Thank you very much, and I hope you liked it.
Thank you very much, Tim, for the presentation. Very useful work. I'm looking forward to try that out myself. For you also answer your questions in Slido, maybe I want to start with one. So in one of the examples you had in your paper, you mentioned that there was a 28 days granularity entered by the user for a monthly pattern. However, as we know, months vary between 28 and 31 days. Isn't that a problem for the algorithm, these irregular granularities?
I think it really depends on the data set. So if you have some small errors between the periods and you don't identify them correctly, you often incorporate this period as well. So in the end, we often identify that this at least brings new frequencies into the system, and it updates some mixture of frequencies, and therefore you see new structures. And if you're not, if the incorporation is not sufficient or you're not agree with that, of course you can reconsider it, and then you can update new ones and just test it.
Thank you. Are there questions in the room? Not so far. So I gotta ask another one. So when you mentioned the selection of the delay that you also have to do, it seems to be non-trivial to select this. Is there any user support for suggesting?
You mean the delay parameter D for the delay embedding? Yes. In the supplemental material, we provide a use case study for the delay parameter D, and we identify that it often is very stable if you are close to some, let's say bounds. We also propose in the paper. So we already provide some lower and upper bounds for delay parameter D, but we also have some suggestions in which area it should lie. And if you follow those rules, it often is stable. But of course, it could happen that it's not stable. But in general, DMD is very unstable regarding the delay parameter D, but if you consider, let's say, these frequencies as we have seen in the links data set, it often produces the same results because we want to enforce such frequencies, and therefore it's more stable. That's also some nice property of our constrained DMD.
Perfect, thank you very much. Let's thank Tim once again for the presentation. So next we have again a virtual presentation entitled Size Pairs, Achieving Stable and Balanced Temporal Tree Maps Using Hierarchical Size-Based Pairing, which is presented by Yunhai Wang and Chang Han.
Hi, I'm Chang Han from Shandong University. I'm glad to share our new technique for temporal tree maps named size pairs. Tree map is a visualization tool that has been widely used in many domains. It depicts a hierarchy as nested rectangles, where each node corresponds to a rectangle and the size of the rectangle encodes the weight of the node. So what makes a good tree map? An elongated rectangle like C will cause the user's perception of its size inaccurate, so it is of poor visual quality. In contrast, a rectangle closer to a square is considered ideal. So the mean aspect ratio usually serves as the quantitative measure of the visual quality of a tree map. Empirical studies have confirmed that elongated rectangles are hard to perceive. They also found that squares are not necessarily better for the perception of sizes. Despite the best aspect ratio is still under investigation, a range from 2/3 to 1 seems reasonable. Tree maps can also be used to visualize temporal data. When the values are changing, the tree map changes accordingly to it. This brings the second measure, stability, for temporal tree maps. The stable tree maps don't move around much when updating, so it's easy to track the size changes compared to the unstable ones. We categorize stability into two types: short-term stability, that is the stability between adjacent time points, and long-term stability, that is the stability across all time. A lot of work has been done on tree maps. Here we just discuss some representative examples. The slice and dice algorithm is the first tree map method. In this algorithm, the tree map's layout is entirely dependent on the data structure, so it is very stable, but the visual quality of the resulting layout is often poor. To overcome this, there have been algorithms proposed to maximize visual quality at each time step, such as squarify and approximation, but their poor stability makes them unusable for temporal tree maps. The ordered tree maps are the first to take both stability and visual quality into account by ensuring that items are always placed close to each other following a certain order. These methods successfully made a trade-off between the two metrics, but the stability is still not very good because keeping the order is not equivalent to keeping the layout. Further, the state-aware tree maps can produce a more stable tree map by reusing the current layout to compute the next one. They start with a high visual quality initial layout made by approximation or squarify, but the visual quality will decrease over time as the initial layout may not fit the value at other time. We can conclude that the key challenge in generating temporal tree maps is the conflicts and trade-offs between the two major metrics. For example, given an initial layout, keeping it stable will cause a decrease in visual quality, while focusing on visual quality will in turn damage the stability. Our goal is to design an algorithm that can make stable tree maps with good visual quality throughout all time steps, while being as fast as possible. The previous methods did not consider the whole time series. In such a case, the conflicts between stability and visual quality are unsolvable. But if we allow access to full data, we can make a better trade-off between stability and visual quality in temporal tree maps. Based on this idea and with the prerequisite of using offline data, we come up with a new technique following a bottom-up approach. Here, we first briefly introduce the pipeline of our method and then go into details. For brevity, we use single-level data to describe size pairs. Multi-level data can be dealt with in a recursive way. The input nodes are first organized by a binary tree, and then we compute the splitting orientation for each internal node to get the global layout tree, which can then be used to generate temporal tree maps. Let's first look at the process of generating this pairing tree. Here, the key question is, why did we choose these nodes to pair together instead of other combinations? How should we choose the nodes that are paired together? Consider nodes with mutually compensating changes are paired together. This will limit the changes to a local region, making the global layout more stable. And it is also obvious that pairing similar-sized nodes can increase visual quality. We call these two criteria compensation degree and size difference. And we choose nodes with high compensation degree and low size difference to pair. By combining these two, we can define a pairing cost between two nodes. Here, omega is a constant. We can make a trade-off between stability and visual quality by adjusting it. We find omega equals 0.5 works well for most datasets. The nodes are then iteratively paired together by computing the pairing cost, and they eventually form a binary tree. After we get that pairing tree, we compute the splitting orientation for each internal node. This orientation is optimized for visual quality and is determined by the median weights of each node. The global layout tree can be used to generate tree maps at each time point because there is an exact mapping relationship between the layout tree and the tree map layouts. Note that we can apply an optional step to flip the leaf nodes on the layout tree to achieve better aspect ratio. The layout tree is a convenient structure and can be leveraged to implement user interactions. For example, label-friendly splitting can facilitate the display of labels, while node repairing can help users compare the sizes without disrupting the global layout. Our evaluation compares size pairs with previous methods, mainly the state-aware tree maps. In this evaluation, we followed most of the practices in the quantitative evaluation paper. Their data taxonomy classifies data in 4 aspects, including the levels of hierarchy, range of node weights, speed of weight change, and insertions and deletions. We use 3 measures to evaluate: the average aspect ratio to evaluate visual quality, the corner travel distance to evaluate short-term stability, that is, the stability between adjacent time points, and normalized location drift to evaluate long-term stability, the stability across all time. In these scatter plots, the nodes near the bottom right corner represents high-quality layouts. 2 variants of size pairs works well compared to the previous methods, especially on datasets with spiky weight changes. Size pairs also works well on long-term stability. One of the reasons is that it can handle reinsertions in a stable way. Compared to the state-aware tree maps, size pairs runs fast, especially for the multi-level dataset. From this animated example, we can observe that size pairs has high stability and balanced visual quality. In conclusion, we present size pairs, a new technique for temporal tree maps that has advantages in visual quality, stability, and running time. And we performed a quantitative evaluation to show that. Thanks for watching.
Hello, everyone. Welcome.
Thank you very much.
Hi.
Hello, can you hear us?
Yeah, I can hear you.
Perfect. There is already one question over Slido. So does your approach also support structural changes in the hierarchy? So for example, introducing new nodes or entire subtrees?
Yes, as we are considering offline data, so addition of subtrees will appear as that the weight of this node or this subtree is 0 before this node is being added. So it also applies to deletions. So yeah.
Yeah, and another question that came to my mind is you wrote in your paper that the computation takes into account all the time steps that the hierarchy changes include. So could it be that if then a new timestamp comes in, that the stability of the whole representation will be broken?
Yeah, if you, I would design this to actually support offline data. So if you use it, it can be used on streaming data, but then it will have no advantages. Maybe the stability or visual quality will be destroyed if new time point come in. Yeah.
Okay, thank you. Is there a question in the room? Okay. Doesn't seem to be the case. So thank you very much for the discussion and presentation. Let's thank the speaker once more. Okay, so next up we have a presentation again in person here, entitled Large NetVis, Visual Exploration of Large Temporal Networks Based on Community Taxonomies, which is or will be presented by Jean Ponciano.
Hello everyone, my name is Jean and I'm going to present our work, Large NetVis, Visual Exploration of Large Temporal Networks Based on Community Taxonomies. I'd like to start talking about networks, which are widely used to represent interactions between domain elements through nodes and edges. Networks are used, for example, in biology, in computer science, in medicine, and several other areas. Visualization strategies help us a lot when you're analyzing network data. The problem is that this visual exploration becomes harder when you are dealing with large networks, mainly because of the visual clutter. There exist different approaches to enhance the analysis of large networks, for example, node positioning, net sampling methods, but even with these advances, visualizing large networks is still challenging. And such a challenge increases even more when you are dealing with large networks that evolve throughout time, the large temporal networks. So I'm talking about large networks and large temporal networks, but I haven't defined what large means. In the context of non-temporal networks, we may find some visualization and non-visualization studies that explore large networks. On one hand, some non-visualization studies, for example this one from Wang et al., consider that large networks are those networks with millions of nodes. In the context of visualization, this definition depends on the user task and other aspects. In this sense, while for some papers, large networks are those with millions of nodes, for other papers, 500 nodes or so are enough to consider a network large. A survey from 2018 evaluated the size of networks in 124 visualization papers, and this survey classifies large networks as those networks with a number of nodes between 51 and 200. In the context of temporal networks, which is our focus, we consider that large temporal networks are those networks with a few thousand nodes or timestamps. There exist some systems for visualizing temporal networks in general, for example, GEFI, the Cytoscape plugin, the NetViewer, and others. But existing systems could be improved in general by providing better visual scalability and guidance, more sampling and filter options, or timeline-based visualizations and multiple views. In this context, our main contribution is LarNet Views. It is a visual analytics system with multiple linked views designed to enable the analysis of small and large temporal networks from global to local perspectives. Our work relies on the concept of communities. A community is a group of nodes that interact more often between themselves than with nodes from other groups. Depending on the network, community may be used to identify friends, co-authors, proteins with similar functions, and so on. Specifically, we rely on 3 existing community taxonomies. This first one, the structural taxonomy, categorizes a given community according to structural patterns, for example, trees, stars, circles, and others. The second taxonomy concerns the overall temporal behavior of a community's internal edges, including their temporal activity, the frequency of these edges over time, and their distribution, how close they are from each other. The combination of these 2 aspects leads us to the 4 categories we see on this slide. And finally, the third taxonomy we consider, And finally, the last taxonomy we consider concerns the community's life cycle and dynamics. So we categorize a given community according to events, such as birth, death, growth, and so on. Let's see the system's workflow. First, the user provides a network of interest and the corresponding metadata, which is optional. The user can also apply some sampling methods and set some parameter values. Then, the system decomposes the provided network into time slices of equal length, and for each time slice, it detects the communities that exist in there. In the next step, the system will categorize the detected communities using the 3 taxonomies I just mentioned. Finally, users can explore communities of interest by using the 4 provided linked views. Let's see a demonstration of the system. To explore a network, we open the menu, select a network, and set some parameter values. This first network contains interactions between students and teachers from a primary school. The system then shows our 2 summary views, taxonomy matrix and global view. Taxonomy matrix summarizes the general network structure, temporal distribution, and evolution by showing the number of communities that correspond to each combination of categories from the 2 selected taxonomies. For example, if you analyze the temporal and the structural taxonomy, we see that there's only 1 community categorized as 3 and sporadically dispersed in the network. Global view uses a grid, where columns represent time slices and rows represent communities, which are depicted as circles. We map the community size using both color and circle size. A click on a cell in the matrix highlights the corresponding communities in global view. Likewise, a click on a circle in global view highlights all the other communities with the same categorization on both views. The system also provides an information panel with general numerical information about the network, community, or node, depending on the current level of analysis. After we find a community of interest, for example this one, we can click on its circle and the system will open 2 local views, the node link diagram and the temporal activity map. The node link diagram shows all the intra-community nodes and edges at once, regardless of the times of the edges. The system shows by default a multi-level diagram when the number of nodes is above a user-defined threshold. Users can explore particular subcommunities and also freely navigate between summarized and non-summarized diagrams. The temporal activity map represents nodes as fixed size squares, and these squares can form blocks in the visualization over time. And thus, they enable the identification of active and inactive nodes and intervals. Back to global view, we see a set of consecutive time slices with few and small communities, which shows us the absence of many nodes in the network. This interval is probably related to the school lunch break, where many students go home for lunch. We also see that the communities are very stable in this network. We have only 1 merge. By analyzing the communities involved in this merge, we see a group of students from class 3B in 1 community, and a group from class 3A in the other. In the next time slice, we have a single community containing both classes. We can also see in the temporal activity map intervals with no interaction. Further investigation might tell us why they occur. Now we see a second and larger network that contains retweets that mention Folha de São Paulo, a famous Brazilian newspaper. This network contains more than 50,000 nodes that were decomposed into almost 2,400 communities, numbers many times greater than those from the previous network. We also see that a default to fit is applied to global view, so it can show all communities at once. This network contains almost 600 communities categorized as star and continuous grouped, including the largest community in this network, which contains more than 2,000 nodes. We open this community and we see that it matches the star type of structure as expected. We conducted a user study to evaluate the usefulness and other aspects of the system. Our study used the feedback of 14 participants who have experience in visualization and network science. 3 of the participants consider themselves specialists in both fields. We collected feedback on many aspects, including whether the participants agree with the statements we see here. The system offers visual scalability, it has satisfactory response time, it is useful, it is intuitive and easy to use. Our results show that most participants agree or strongly agree with the visual scalability, and that all of them agree or strongly agree with the other statements. Regarding the usefulness of the system, one participant commented, for example, the system is very useful for dealing with unknown data in an exploration stage. According to another participant, if I'm interested in a certain structure, I discard the others and optimize time and efforts. We also asked them to evaluate the 4 provided views. We can see that most participants think the views are useful, and they prefer global view and the node link diagram over the others. I'd like to mention now some limitations and ideas for future improvement. First, we intend to extend the system so we can have a single community belonging to multiple categories in the structural taxonomy, which is not possible in the current version. We also intend to incorporate more node and community positioning strategies, as different strategies highlight different patterns. And finally, we intend to adapt the system to make it useful for analyzing very large networks, for example, those with 1 million nodes. You can find the paper and system through this QR code, more information on these 2 websites. Thank you very much for your attention.
Thank you very much for the presentation. The floor is open for questions. There's one coming in from Slido. So does the system suggest a number of time slices to help the user in this exploration?
The number of time slices? Okay. We don't recommend a specific number of time slices, but we do recommend a range of possible time slices for analysis. And for that, we use a non-uniform time slicing approach from a previous work. So we run this method under different configurations, and we use the outputted range as possible time slices for the user to use.
Okay, is there a question in the room? Yes.
Yeah, I have a question about your argument or reasoning about scalability. So my understanding is it's kind of linear in the number of communities. So it doesn't seem to be that scalable because you showed like 2,000 communities to follow. For me, that's not scalable. I would have expected some hierarchical structure over the communities. Is that in the system or planned, or so could you comment on that scalability? And like the follow-up to the other one, is there also a kind of a similar mechanism for scalability in time? So if you have lots of time steps.
Okay, so we work with networks with a few thousand nodes or timestamps. So we don't expect too many communities. But we now intend to extend the system to make multi-level approaches in the community detection also. We have now only multi-level approach for the node link diagram. We intend to adapt the other views as well to consider a higher number of communities.
And the other one was about time scale. Let's say if you have a very fine-grained temporal sampling, because it seemed to be discretized in time and linear there.
It depends on the natural characteristics, of course, but we don't apply different temporal resolutions. We just aggregate into a predefined number of time slices. So in the current version, it's up to the user to define which number of time slices would better represent the interval on the granularity you prefer to analyze.
Thank you.
Okay, thank you. Is there another question? Okay, this doesn't seem to be the case. So thanks a lot for the presentation. Which brings us to the final talk of this session, which is entitled ASTF, Visual Abstractions of Time-Varying Patterns in Radio Signals, which is a paper that also received an award.
Hello, everyone. Welcome to my presentation. I am Genghui Bai from Central South University. This is the agenda. The first is motivation. A radio signal can transmit and receive information through space, but must occupy a contiguous section of the electromagnetic spectrum. The spectrum is a finite natural resource, thus, radio communications must be supervised to ensure orderly spectrum usage, especially for airport and seaport. Analyzing radio signals with a time-frequency diagram is the daily work of radio supervisors. Here is a TF diagram. Its y-axis is time, x-axis is frequency. A blue band indicates that the spectrum section is occupied by a signal for communication. In this diagram, 3 signals can be found. The first is a constant signal, the second lasts for a while, the third occurs twice for a short time. Traditional TF diagrams can only display short-term spectrum monitoring data at a time due to a space-limited screen. A straightforward solution is to use a scrolling manner. However, radio supervisors must patiently browse an entire time span to reconstruct the time-varying communication patterns of signals. Potential solutions include sampling and aggregation. However, short discontinuities or short communications could be not visible due to the loss of information, thereby misjudging time-varying communication patterns in signals. For example, short discontinuities cannot be seen in red areas. Short communications are not very clear in orange areas. We propose a new visualization named Abstracted Signal Time Frequency Diagram, ASTF, to solve this problem. For example, in our ASTF, Figure D, short discontinuities can be seen in red areas. Short communications are indicated in orange areas. Before data processing, we need to introduce related concepts to signal communication states. A signal has 2 communication states, namely, appearing and disappearing, at a specific time. We use number 1 to represent appearing, and use number 0 to represent disappearing. A signal has 2 types of communication state change points. Rising edge is from disappearing to appearing, falling edge is from appearing to disappearing. A time-varying communication pattern can be regarded as a CSCP distribution. A CSCP distribution is formed in a binary sequence. Our data processing has 3 steps. The first is signal identification. Radio spectrum data are semi-structured to record amplitudes of frequency points, but do not directly provide signal information. We convert radio spectrum data into fully structured radio signal data. A record of radio spectrum data consists of a timestamp, signal ID, and the 4 basic characteristics of a signal, namely, center frequency, bandwidth, strength, and signal-to-noise rate. The second is to extract the binary communication state sequence of each signal from radio signal data, and the last is to extract the statistical outliers. In visualization design, we first introduce the basic layout of ASTF. The x and y axes are frequency and time, respectively. A straight stripe along the y-axis is a signal. The stripe's width and midpoint on the x-axis are the signal's bandwidth and center frequency, respectively. The color is the signal strength. The visualization of time-varying communication patterns of a signal is the focus of this work. Our idea is: First, divide the entire period of a binary sequence into n slices. Second, divide the entire timeline in a display into n corresponding cells. Last, use visual encodings in a cell to represent the CSCP distribution in a slice. The main challenge is that too many possible CSCP distributions exist in a slice. Our solution includes 2 steps. Step 1 is to use an agreement and 3 bases to classify possible CSCP distributions into 10 classes. Please see our paper to find details. Step 2 is to use 4 visual encoding rules to encode the 10 CSCP distributions in a cell. In brief, blue indicates the appearing state, blank indicates the disappearing state. A triangle indicates a CSCP and its direction indicates a rising or a falling edge, and a triangle with slope lines indicates multiple CSCPs. Please see our paper to find details. Here are the visualization results of 10 types of CSCP distributions. For anomalies, we use red lines in a cell to represent the occurrence of anomalies in a slice. Here is a demonstration of ASTF and some alternatives of visual encodings. Segmenting a binary sequence is an optimization problem. The optimization goal is to reduce the information loss of CSCP distribution in visual space. The challenge is how to quantitatively determine the CSCP distribution in visual space. Because in visual space, CSCPs have been encoded by triangles, and there are no exact locations. 2 principles are proposed to address this challenge. We use the principle of midpoint equivalence to determine the location of a CSCP in a cell. For example, in cell 1, the leg midpoint of the triangle is at 2.5 seconds on the timeline of visual space, which is the location of the corresponding CSCP in visual space. While in slice 1, the actual occurrence time of the CSCP in data space is at 4 seconds, thereby resulting in information loss. We use the principle of area equivalence to determine the duty ratio of a signal in a cell. For example, the duty ratio of the signal in data space is different from that in visual space, thereby resulting in information loss. According to the 2 principles, we defined 3 metrics. They are the similarity of CSCP distributions between data and visual space, the difference of duty ratios between data and visual space, and the coefficient of variation of time spans of slices in data space. Now, we can define a loss function. It is an expression of the optimization goal of the time segmentation algorithm. We designed a new algorithm, named BSSVA, to segment a binary sequence of communication states of a signal into time slices with a 2-strategy optimization. In stage 1, we evenly divide a sequence into n subsequences and traverse the n in a range to get an optimal n that achieves the minimum loss. In stage 2, we take CSCPs as feature points. We adjust the locations of original diving points from stage 1 based on feature points, and obtain the optimal dividing points that achieve the minimum loss by gradient descent. In evaluation, we conduct an algorithm performance experiment with 5 reference algorithms. Our algorithm obtains the smallest losses among all references on all datasets, and it can complete the segmentation process with acceptable time costs. We also conduct a user study. 3 visualizations are involved. 30 participants are divided into 3 groups. Each group uses only one of the 3 visualizations. Each participant answers 18 objective questions by observing visualization results. For example, by viewing this ASTF diagram, the participants need to answer which signals present periodic communication patterns. The ASTF group obtains the best accuracy and time performance, and the ASTF diagram obtains the best subjective ratings. Please find details in the paper. We demonstrate 2 application scenarios in radio signal analysis. An ASTF diagram could act as a superior view in a multi-viewed interface to provide an overview of signals with a large time span. Users thus could select a short time span of interest in the ASTF diagram to update a TF diagram to observe details in raw radio spectrum data. ASTF diagrams could provide semantic interactions on signals to fulfill advanced analysis tasks. For instance, when comparing the communication behaviors of two signals, users could select the two signals to filter out the other signals in an ASTF diagram and then juxtapose them closely to facilitate the comparison. Moreover, our visual abstraction method and BSSVA algorithm can be applied to visualize long-term binary sequences generated in various domains. For limitations. First, the scalability for frequency is not discussed in ASTF. Second, there are some little problems when displaying special data. Third, the BSSVA algorithm cannot be directly applied to streaming data in current. Last, the performance of BSSVA algorithm could be future improved. In conclusion, we propose a new diagram, ASTF, for long-term radio signal analysis. We also propose a visual abstraction method and time segmentation algorithm which could be applied for visualizing common long-term binary sequences. Thanks for your listening. Please find this work at GitHub.
Hello. Hello, Gangwei. Can you hear us? No. Gangwei, can you hear us?
Yes.
Perfect, perfect. Thank you very much for presenting your work, and congrats to the Honorable Mention Award for that paper. Are there any questions in the room? To start with, no? Okay, then I might start with one. So I was interested in the larger analysis process of the users you were talking about. So what for are they using these diagrams? What's the larger work progress around that?
To achieve the performance, we conduct lots of experience and experience with radio experts.
Which tasks do they have to fulfill, and which tasks are they using the diagram for?
Radio single analysis.
Sorry, I didn't hear the answer.
I can't hear the
So could you say that once more?
Yes.
Okay, so there seems to be an audio problem. You might want to repeat the answer.
Yes.
Did you get the question?
I can't get clearly.
So my question was geared towards the larger work process that your analysts are involved in, and what are they using your new diagram for?
They are used for video single analysis, and they can use it apply it for the visual visualization of any other binary sequence.
I see. Okay. Are there any other questions here? Okay. And in the last part of your presentation, you were showing some interactive means so that one could also do some exploratory task with it. Was that part of the user study, or did the users in the study only use a static version of the diagram?
the user study we conduct with the graduates and I can't get your clearly. Get your question clearly.
So at the end of the presentation, you've shown some interactive features of your tool. Were they part of the user study or not?
Yes.
Yes, in terms of they were part of the user study? So did the users in the study work with an interactive version or with a static version of the diagram?
Sorry, my English is poor. I can't understand your questions.
Okay, so I might try in written form then on Discord, and you might want to answer that question there then. Okay, so thanks once more for the presentation. And this also concludes the session on temporal data. Thank you very much for listening, for participating in the discussion, and have a nice day.